Okay. Thank you very much. So I see we are many. So I mean, what I would like to do in half an hour is just to give a very brief and general introduction to the electron-phonon problem and what can be done in Yambo. And because of course 30 minutes is absolutely not enough. I mean, is a word itself, electron-phonon, both from the many-body perspective and also from density functional theory. So, I mean, a super big field. So I will just give a brief introduction with the main reference so that whoever is interested can read more and get more informations from either the Yambo documents and this reference. Do you see it?
Yes.
Okay, lovely. So finite temperature calculations with Yambo. So first of all, why? So why do you need this finite temperature? Well, actually, it is pretty known from standard intuition that most of the experiments, actually all experiments, are done at finite temperature. So in general, actually, the temperature is a hidden parameter in the papers. So I don't know if you had this experience, but sometimes when you read the paper, you actually don't know what is the temperature that the experiment was performed. This is because from an experimental point of view, it is very difficult to control the temperature. And most of the experiments are done at a room temperature. And also because the effect of the temperature in general is believed to be mainly, broadening of the excitations. I mean, this is just a consequence of the simple intuition that when you have a finite temperature, atoms are just vibrating. But as a matter of fact, if you want to be predictive and actually accurate, you cannot disregard the effect of temperature. So, for example, there was this paper in 2004 where the same system, it is studied both from the point of view of absorption and luminescence. And the funny thing is that in the same experiment, in the same paper, they were using two different temperatures. And again, this is because of the experimental apparatus that must be able to be attached to a cryostat to control the temperature. And so actually, the temperature was playing a big role in even in the first paper, in the first studies of excitonic effects. So this is the famous paper by Cardona when they measured the finite temperature spectrum of silicon for several temperatures. And well, actually, Cardona has been a very, very, very impactful physicist. Actually, he was one of the few able to do both theory and experiment. And this phrase that is actually supposed to be referred to him, that was saying, unfortunately, theorists don't even bother to compare the calculations with low temperature measurements using more easily accessible room temperature spectra. And this is true. In one of the first calculations of the absorption test of silicon, they compare with the wrong spectrum. So they just got this paper and took the I don't remember if it was the 243 Kelvin curve and not the low temperature, because in general, if you are not including any effect, you're doing a poorly electronic theory, you should compare with the low temperature measures, even if actually this is not formally correct, because as we will show in a second, even when you reduce a lot the temperature, you never reduce to you can never get rid completely of the phonons. In any case, this finite temperature absorption of silicon, and there are many on the market. I mean, if you search in the literature, you will find many different experiments done at finite temperature. You see that the modifications are actually quite remarkable. So if you increase the temperature from 30 Kelvin to almost 800, the absorption gets more and more broad and actually moves towards lower energy. Now, if you think in terms of energetics, 793 Kelvin are around 70 millielectron volt. and the quasi-particle gap of silicon is 1,200. So you are really in an order of magnitude of energy where electrons are not feeling anything. And then already from this figure, you can deduce that actually the effect of temperature is sizable. Even if it is actually accessing very low energy excitations, this is very, very much visible in the experiment. Okay, so at the end of the story, the movement of atoms, actually, it is something that intuitively you should know very well. I mean, now, even if you take a fully interacting system with real atoms and blah, 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 in general, you can rewrite the phonon problem as just a series of free oscillators, harmonic oscillators. Then now you introduce those harmonic oscillators, is tricky, but I mean, at the end of the story, this is the final result. I mean, the phonon bands you see in the experiments, in nuclear scattering experiments, are just those frequencies of the oscillations of the atoms around some high symmetry directions. But now, if you do a simple theory of an harmonic oscillator, and then you define it in harmonic oscillator the mean displacement square, so this is just U as the displacement, is just the quantum observable that describes the displacement of the atom from the equilibrium position. Then, of course, the average of U is 0, but average of U square can be proved on a piece of paper that goes like 1 plus 2n, where n is the population of that oscillation. The 1 is quantistic thing, isn't it? I mean, if you do the classical limit, you get 0. I mean, if you think on a classical oscillator oscillating, and then you reduce the temperature in the sense that you reduce the amplitudes of the oscillation, well, you can reach a point where the sphere is still. So it's not moving anymore. This means that it's purely classical. From a quantistic point of view, instead, if instead of an oscillator you have a real atom, well, the atom maintains a finite spread, even when the temperature goes to 0. It is this 1. This is the 0-point motion effect. The 0-point motion effect actually causes the nucleus of any atom to be actually not well defined in position. So it could be here as it could be here. This is simply means that even if when you do a DFT calculation with PWSCF, in the input file you specify the position of the atoms, in reality, this is not true. This is a classical approximation. In reality, the atoms have a wave function themselves. This wave function is as large as this mean square displacement. And this displacement, actually, you can think, using statistical arguments, as the atoms sitting in different positions. Now, I may ask you, well, what happens if in a given system you do calculations moving the atom by hand of a super tiny quantity, but moving it? Well, you will get the gap, the optical properties, everything will change. So the message of this simple slide is simply that regardless of the temperature, even if you decrease enormously the temperature, you always have an indetermination in the position of the atom, and consequently an indetermination in position of the gap, of the absorption gap, of the current, or you name it, whatever. Everything you could calculate is not univocally determined by the position of the atom, because there is an intrinsic 0-point broadening of the atomic wave function that leads to an indetermination. And this is really one of the most sharp manifestations of the quantum nature of electrons and materials. Now, how do we do it? Well, of course, you need a many-body theory for that, because it, again, is a many-body problem, where the many bodies are the electrons and the phonons. So now, briefly, very briefly, I will just go through the three different basic aspects of the electron-phonon problem seen from an ab-initio perspective. So we will introduce shortly tolerance, then see how the excitons are affected by temperature, and then if there is time, I'm not sure, I would like to conclude with some specific feature connected to the electron-phonon problem. Okay, so very briefly, before even touching Yambo and do electron-phonon calculation, you have to understand that Yambo is based on DFT as far as electrons are concerned. For phonons, Yambo is based on density functional perturbation theory. So you can have a look at the review of Baroni to understand what it is. Density functional perturbation theory is just the DFT framework extended to a perturbation. So if you think of the system perturbed by moving by hand an atom, or by applying a pressure, or by hitting with a hammer the material, and then if this perturbation is not so strong, you can actually rephrase the DFT theorems in this perturbed system. This is density functional perturbation theory. As a matter of fact, at the end of the calculation, you don't get just the electronic levels, but you get the phononic energies and the electron-phonon matrix elements. I will tell you at the end how you can practice this using Yambo tutorials. I will just tell you at the end of this lecture. Now, as far as electrons regards, well, you have that the electrons actually feel that the atoms are oscillating. The very beginning, the very original theory of this electron-phonon interaction, there is a standard perturbation theory approach, was devised by Allen and Cardona. So Cardona, as I told you, is an experimentalist, but he did theories. There is a theory named to him. Is Heine, actually is Heine Allen Cardona approach, because Heine Allen and this is Allen, Tim Allen, and Phil Allen, and as Manuel Cardona, but also Heine in a parallel paper devised the same approach. So I mean, this is something that is, you don't need Green's function. You can review it on this paper. Is standard perturbation theory, Rayleigh Schrödinger perturbation theory. You take your Hamiltonian and you perturb it, first order, second order, by moving the atoms. It's just first order and second order variations of the Hamiltonian. You do perturbation theory on top. Really, Rayleigh Schrödinger. I mean, what you can study at the course of quantum physics at the university. Rayleigh Schrödinger perturbation theory. If you do Rayleigh Schrödinger perturbation theory, well, you get that the variation of the energy that can be evaluated easily is just given by this object. Well, this object has as ingredients the electronic energies, the electron-phonon matrix elements, and the phonon occupation numbers. So you see this n+1. When n goes to 0, you have a finite change in electronic energy due to the, indeed, 0-point motion effect. So this is something that is coded in Yambo. It has been used actually to publish stuff. So the story begins in 1992 and 2005, where those calculations were done using some empirical methods. Then in 2008, there was one of the few, the first papers that I did to do everything in an ab-initio scheme. So with density functional perturbation theory, to reading stuff from density functional perturbation theory. And this was indeed the finite absorption of silicon. And then several other papers, just at the beginning. So with Elena, that was my PhD student at that time. We studied a polymer, so to see what is the effect in the case of nanostructures. And then, but after 2011, many other papers appeared. This is, I mean, it's absolutely not wants to be a total review. Okay, so, but I would like to give you, rather than an historical review, a conceptual review. So now, where is the electron-phonon actually effects coming from? Well, always from the self-energy. So always from there. So at the end of the story, the electron-phonon effect is just one contribution to the self-energy. So GW, you have seen GW, in the tutorials, you have seen the screen exchange and everything. But I mean, if you include electron-phonon corrections to the self-energy, you get the new self-energy, and through Dyson equation, you get the corrections to the levels. Now, in general, this correction can be tiny or large, depending on the strength of the interaction. If every time I will go back to this size of the corrections in the specific case of the electron-phonon problem. If you do the self-energy approach, so then if you go on the literature and then you see how to derive the GW self-energy in the case of the phonon interaction, well, you can realize that actually the Eine, this is Volter Eine, the Eine, Allen, and Cardona theory is just an adiabatic limit of the self-energy. So when you take this is Lundqvist, Stig Lundqvist, this is Larsedin. When you take the many-body approach, and then you can find the standard Eine and Cardona theory as a static limit. If you want, the Eine and Cardona limit is the screen exchange, is the corresponding of the screen exchange for GW. So a static correction. Good. So this is for quasi-particles. This is something in Yambo it is coded. You can calculate with a procedure that goes through PWSCF and Yambo the temperature-dependent gaps and lifetimes, and then with Yambo you can even calculate the temperature-dependent absorption. How is this done? Well, the theory gets a little bit more complicated, but I want first to give you something that, I mean, in inspiration that you can easily verify with the tutorials that we have provided. So you have calculated in several tutorials the absorption spectrum with a Biesa-Peter. Surely in my room yesterday we discussed of this damping parameter. There is this damping parameter that is put by hand. Now I invite you to do a calculation setting this damping parameter to 1 millielectron volt. That's a parameter that theoretically, and I tell you, should go to 0 at the end of the calculations somehow. But if you don't introduce electron-phonon interaction, send it to 0, Yambo will give this horrible thing, just lots of delta lines, delta peaks, delta peaks. This is because the Biesa-Peter Hamiltonian is an emission or quasi-emission, anyway, is emission to first approximation object. So the eigenvalues are real, so not damping. But the experiment is wide, is very much broadened. And this is due indeed to the effects of this. This is a horrible slide, I know, just get it as a cartoon. So the self-energy actually enters in several steps the Biesa-Peter, and at the end of the story, what it does, it broadens the basis where the Biesa-Peter is written. Actually, Biesa-Peter is written in the basis of electron pair. Well, if you introduce within certain approximation the electron-phonon self-energy in the machinery, you get that instead of that quasi-Hall and quasi-electron basis, you get a quasi-Hall and quasi-electron polaron. So I mean, the electrons and the hole that you use to describe the axiom gets broadened. They get, you know, the big fuzzy, so you don't see them very well because of the 0-point motion. Well, if you do that, you get that actually your absorption experiment will actually depend on the temperature, because the more you actually populate the phonons, more you increase the temperature, more the width of the electron pairs will increase. And actually you can prove on a piece of paper that if you increase them large enough the temperature, the Bose factor in the theory will give a linear explosion of the temperature. Of course, above a certain temperature, you have anharmonic effects entering in the story, and then everything gets more and more complicated. Lovely. So how much time do I have? Well, what is the timing? Someone control the timing?
30 minutes should be.
I am at 30 minutes now.
No, no. You have
a 10 minutes. It's okay.
Yeah,
5 10
minutes.
minutes.
Exactly.
Oh, 5 10 minutes. Okay, so I will go just through. This is just for to give you an idea of something that, in my understanding, is a peculiar difference between the electronic correlation and the phononic correlation. So even without knowing anything about many-body and blah, 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 you can actually intuitively see that the phonons have a much lower energy compared to electrons in a semiconductor, of course. So a phonon can be in silicon. So in general, the phonon energy can be evaluated with the bi energy, that is the energy of the maximum phonon frequency, and it is the maximum phonon frequency. And in silicon, it's 60 millielectron volt. Can be 100, can be 200 millielectron volt, but in general, it's much lower than the gap. So this means that when you do the GW approximation, and then you want to produce a quasi-particle approximation, then you have to translate all arguments used in the electronic case to the phonon case. But you have a big problem, because the quasi-particle approximation in the electronic channel is based on the size of the plasma frequency. The plasma frequency in silicon is 20 eV, 21, something like that. So it's large. Because of that, you can say, wow, when I plug this thing in the self energy, well, the self energy gets those peaks very far from the gap. And in the gap, I just see a very smooth object. Actually, with the phonons, this thing is not true anymore, in the sense that the phonons can produce peaks in the self energy very near the gap, actually, with a very super tiny frequency. So this means that it can eventually break the quasi-particle picture. So this means that the quasi-particle is a peak in the spectral function. It's not a delta thing. It's not even a Lorentzian, but gets something really structured. So this means, physically speaking, that the electrons loses its individuality. So the electron is not able anymore to live alone in a material, but actually has to move around a material carrying on the shoulders a lot of phonons around it. That's just blurry is how you see it. Actually, this was, and then I actually do really invite you to read this paper. This is by Englishberg and Schaeffer. Schaeffer is the guy of the Nobel Prize BCS, where they just studied in this paper the homogeneous electron gas, the fund self energy in homogeneous electron gas, studying different regimes of the interaction. This is a very pedagogical paper. So you can actually understand the electron-phonon problem by doing the math of the paper. And then you see that actually the spectral function, by increasing the strength, gets surely a quasi-particle peak here. And also here is this peak, this big arrow is the quasi-particle. This is super tiny, 0.06, 0.15, increasing the interaction. The side band of the phonospectral function, of the electronic spectral function, gets larger and larger and larger, up to the point where it is comparable with the quasi-particle peak. So this was something that actually, oh, sorry, I didn't put it on. I'm sorry. Yeah, this was something that was exactly the subject of the work that Elena did, where we proved that in those materials, actually quasi-particles disappear completely, so you don't have bands anymore, and it gets really blurry, and you can talk of a perturbative polaronic state. So let me just conclude with two things that's important. Okay, one is, I mean, the electron-phonon problem can count on a very long history because, of course, of the of the superconductivity. So there are books on the electron-phonon problem on homogeneous electron gas and actually applications for superconductivity. But in 2017, Feliciano Giustino did this review where actually it is studying the electron-phonon problem from first principle. So you can find there millions of references. But the most important thing is that we have a brand new tutorial that is thanks to Elena, and I know to Claudio to what extent, but thanks to the the Yambo family in France. And so this tutorial is something that you can use. And then let me say, do you see my, still my, where am I? Yeah, here. Do you see my screen yet?
Yes.
Lovely. So you can go on the wiki, and there is here in the overview, you find in the standalone tutorials, the electron-phonon coupling. Here it is. And here there is everything. This morning I did it again, and it's complete. And here you can see that, and with this I conclude, the calculation of electron-phonon effects in Yambo is more involved compared to the standard GW calculations, because you need a ballet of PW components and Yambo. So it is a structured procedure that is perfectly described in this tutorial. So you need to calculate first PW, and then you need to calculate the phonons. And this actually, you can easily realize this is the most heavy part of the story. Calculation of the phonons, the organization of the density, or the dynamical matrices. And yes, you get phonons, then you get to do a calculation of the DBSCF, so of the electron-phonon matrix elements, again, using PW. So it is self-consistent, phonons, DBSCF, and then you have that you can put everything together using YPP and using Yambo, and obtain the databases, the electron-phonon databases that are read by Yambo to do all consequent calculations. And then there is a run level in Yambo PH that you can use to calculate within the fine approximation for the self-energy the quasi-particle properties of selected bands. And then you can obtain nice things like this, like the gap, or in general, an energy as a function of the temperature. In this case, it is the gap for this grid of silicon as a function of the temperature. And then from there, you would see that in general, being a correlation effect, the gap is reduced, a part of anomalous systems where actually it's the other way around. But in general, in the case of semiconductors, the gap is reduced. And so you can actually see this linear behavior for large temperatures. And then there is also another, you can even calculate optical properties, finite temperature, again, very much well described. And then you see that, as I was telling you at the beginning, those delta peaks gets broadened and actually moving towards lower energy. This is a very non-converged calculation, but it is clearly pointing to the effects that you will find in a realistic calculation. And with this, I invite you to then remember, you have this review. So study before running, don't run before study, because then you can play the numbers on a lottery. So study and run and practice with the Yambo tutorials. And then of course, use the code you want. I mean, there are other codes in the market that can do this kind of things. EPW, also Ab-init, I think to do, Ab-init, yeah, no, sure, Ab-init. So pick up the code that you prefer, but study first. And with this, I thank you for your attention.